Hi everyone, welcome to the session. Let's get started. Have you ever wondered, why does a diamond sparkle? Before we answer that, let's see something cool.
I have with me here a piece of glass which is cut like a diamond and a laser. Now look what happens if I shine the laser into the glass. Wow, amazing, isn't it? Look at all these beautiful patterns. Now what's causing all these bright spots? Let's find out.
What you just saw there was due to a phenomena of light called total internal reflection. Now, let's understand what is total internal reflection. So here is a simple setup. It's a round bottom flask filled with water, and there is a laser directed from the bottom. Now we know that water is a optically denser medium compared to air, right? Now watch. You can see that as the ray is traveling from denser medium to the rarer medium, it is refracted away from the normal, right? Now, if I increase the angle of incidence in the denser medium, the angle of refraction also increases. Now, at a particular angle of incidence, you can see this. Now, at a particular angle of incidence, the angle of refraction becomes 90 degrees. That is, the refracted ray just grazes over the interface between the water and the air. Now, this angle is called critical angle. Now, if I increase the angle of incidence beyond the critical angle, you can see that all of the incident light is reflected back into the same medium, even though there is no mirror here, right? Now, this phenomenon is called total internal reflection. Let's understand total internal reflection in little more detail. So here you can clearly see the path of the beam here, right? It is going like this. Now, at the point of incidence, you can draw a normal and indicate the angle of incidence and angle of refraction as well. Now, you can clearly see that the angle of refraction is more than the angle of incidence, indicating the fact that it is refracted away from the normal. Similarly, if I increase the angle of incidence, right, you can see that the angle of refraction also increases. Now, at a particular angle of refraction can become 90 degrees. That is, it just grazes over the interface between the two medium. Now, that angle of incidence is called critical angle. Now, if the angle of incidence is greater than the critical angle, right, here I is greater than the critical angle, then the incident ray is completely reflected back into the same medium, right? Now, this is called total internal reflection. Now, let's see a relationship between critical angle and refractive index. So now here you have two media. So this is medium 1 and this is medium 2. Let us say the absolute refractive index of medium 1 as N1 and medium 2 as N2. And as you can see, the ray of light is traveling from N1 to N2. And also let us say that the refractive index of N1 is greater than N2. So the angle of incidence is in the denser medium. So it is, as it is traveling from denser medium to the rarer medium, it is refracted away from the normal. Now, using Snell's law, right, we can write N1 sine I is equal to N2 sine R. Now, what happens if R becomes equal to 90 degrees, right? See this picture here. So, when the angle of refraction becomes 90 degrees, that is, the refracted ray just grazes over the interface, we say that the angle of incidence in the denser medium is critical angle. So we can say the incident angle is equal to the critical angle. So we can write N1 sine IC is equal to N2 sine 90. Now sine 90 is equal to 1. So you get sine IC is equal to N2 by N1. Right? So this is the relationship between the critical angle and the refractive index of the two medium. Now suppose if the medium 2 is taken as air, then the absolute refractive index of air is 1, right? So N2 becomes 1. So we get sine IC is equal to 1 by N1, right? So that is, as you can see, if the absolute refractive index of N1 increases, then the critical angle decreases. So higher the refractive index, lower will be the critical angle. So now if the angle of incidence is greater than the critical angle, so we know that the light ray will undergo total internal reflection and it is reflected back into the same medium, right? So this phenomenon is basically called total internal reflection. Now let us solve a simple exemplar question quickly. So the question says, for a ray of light entering water from glass, what is the critical angle? So the refractive index, that is the absolute refractive index of water, is given as 1.33 and that of glass is given as 1.52. So you can see that glass is optically denser medium compared to water here, and from the figure you can see that the ray of light is traveling from denser to the rarer medium, so total internal reflection can take place. Now here it is incident at an angle of at critical angle, so the angle of refraction is 90 degree. Now applying the formula we just derived, sine IC is equal to N2 by N1. So N2 is the refractive index of water, which is 1.33, and N1 is the refractive index of glass, which is 1.52. So sine IC we get 0.875, and then sine IC is equal to sine inverse 0.875, which is equal to 61 degree. Right? So the critical angle for these two given pair of media comes out to be 61 degree. So now let's come back to the question we started out with. So why does the diamond sparkle? See, there are two main reasons. The first one is diamond has a very high refractive index, which means it has a very low critical angle. So it is about 24 degrees. And the second reason is the faces of the diamond, right, are cut in such a way that any ray which enters the diamond is incident at an angle greater than the critical angle, and it will undergo multiple total internal reflections within the diamond before it emerges out of one of the faces or corner or maybe an edge. Now this causes the diamond to sparkle.